Hello everyone. So let's solve this LeetCode medium problem. Minimum sum after divisible sum deletions. So the problem states that we are given an integer array nums and an integer k. Now we can repeatedly choose any contiguous subarray of nums whose sum is divisible by k, and we can delete it. Now once we have removed that particular subarray, so suppose this was the entire array and we remove this segment. So once we remove it, this segment and this segment will be merged together. Okay, means the remaining elements will be closing the gap. Now again we can choose again some segment and remove the segment if the sum is divisible by k. Now we need to return the final minimum possible sum of nums that we can get after performing this operation, means any number of times. We can perform this deletion operation any number of times. And we are given that the size of nums as well as this k can go up till 1e5. Okay, so let's see the given input. So we are given that 111 and k is equals to 2. So for 111 we can remove some segments whose sum is equals to 2. So either we can remove this segment or this segment, or what, these segments only. Okay, so if we remove this segment, the remaining array will be 1 and the sum will be 1 only. So this will be the minimum sum that we will be able to get, and hence the output here is 1. Okay, let's see another input. So we are given 31415 and the sum with that we can delete is equals to 3. Okay, so either we can delete, we have the array as 31415. So either we can delete this 3, then the remaining array will be 1415. Now can we remove further segments with sum divisible by 3? So sum means this is the k, and sum should be divisible by 3. So let's see, if we see for 3 will may not be able to get any subarray. For 6 we have this particular subarray, right? So if we remove this segment, the sum is 6 and 6% 3 is equals to 0. Hence the new remaining array will be 5, and means this will be the minimum sum that we will be able to get. Hence the output here is 5 only. Okay, so what do we need to do? We in a brute force manner, if we try to do it, then we'll pick some subarray, delete it, and then sum the remaining array together, and then perform the same operation on the remaining array. So we know if it will try to do it recursively, we'll need to do it in a recursive fashion, such that we perform the operations and then merge the two arrays and then perform the operation on the remaining new array. Okay, so since we need to perform the same operation again and again, so we can do it in a recursive fashion. But obviously that will since in this case the ways of choosing indices will means the depth of tree will go up till n, and at each step it will be divided into n minus 1 and so on. So this will be of the order of n factorial complexity, obviously. Okay, so obviously that will not be allowed because n can go up to 1e5 here. So what can we do here? So we know we need to minimize the sum, means minimize the possible sums. So one thing that we can do is we can suppose if we have this subarray, and from 0 till I, what you can try to do is we try to maintain some value, such that means we apply operations in such the way such that the sum of remaining numbers is means as minimum as possible. Okay, so we store dp of I is the minimum sum after removal. Okay, but obviously if you want to find out this minimum sum, we'll need to know what elements we are removing. Okay, then the elements that we remove, suppose that is elements that we remove has sum 1, then this mini will be simply total sum minus the sum 1 that we have removed, right? So obviously if you want to find this minimum sum, then we will definitely need to calculate the maximum possible, the maximum sum that will be deleting. Okay, so we'll need to delete this means the sum 1 value should be as large as possible, so that this minimum value is as minimum as possible. So we got to see that instead of finding out the minimum possible sum, we need to definitely calculate this maximum possible sum that we can delete. Okay, so from that what we can observe here is we can observe that minimum remaining sum will be nothing but the total sum minus maximum of the deleted sum. Okay, this is already you have observed, means for finding this minimum remaining sum we should be maximizing the deleted sum. So what if we try to write the dp in the form of this value, and why we are moving in the direction of dp? Because we know each element, means each element here, if it belongs to a subarray, it will have either a choice of being included in a subarray which is getting deleted, or like not getting included. Okay, means the subarray has formed in this way. Okay, so each element has a choice. So like we can iterate through all possible ways of these choices using DP only. So that's why we are moving in the direction of DP, and like trying to think about the DP state and see like whether the intuition is correct or not. Okay, so let's define the DP state as the maximum sum of deleted elements we can achieve or considering only the prefix nums 0 to I. Okay, so the prefix DP of I simply means that from the index 0 till I, what is the maximum possible sum that we can delete. Okay, such that like maximum possible sum such that we can delete means it should have like we deleted in such a manner. Maybe we can delete some continuous functions. So like let me discuss a doubt you might have. Like what if we have the array from 0 to L minus 1, what if we simply like remove the maximum subarray, max subarray, with some percent k equals to 0, with some percent k equals to 0. So you might think like this may give us the means optimal output, because we will simply remove that subarray with the longest means maximum sum, and then the remaining array will have the minimum sum. But suppose k was like 100. Okay, and the array was 100 100 1. Now when you try to find out the maximum subarray which has like some percent k equals to 0, this means sum should be either 100 200 300. So you will get the maximum subarray as 100 only. Okay, this 100 or this 100. So you will know like if you find the maximum subarray, then the remaining array it will be 1 1 100 1. So we know like we will need to remove this disjoint subarray and this disjoint subarray separately, right? We cannot remove a maximum subarray continuously and then we'll getting the optimal output. Okay, so that's why we are like doing this. So that's why this approach will not work here. And similarly, like if we try to, you might think like we can remove the maximum prefix from the left and the maximum suffix from the right, and then this minimum value will be like minimized. So obviously this will also not work, because like in these scenarios as well. For example, it was like suppose 100 100 100. So you will remove this, but you will not remove this middle part. Okay, so hence for these scenarios, whether like to handle these scenarios, we are heading in the direction of DP, because it will automatically handle all these scenarios of like getting picked up or not getting picked up. Okay, so we define the DP as the maximum sum of deleted elements we can achieve considering only the prefix from 0 till I minus 0 till I. Now we need to find the transitions that we have. So for each nums of I, we have either choice of deleting it, means not deleting, or deleting it. So if we do not delete it, then it will be simply like the maximum sum that we'll have deleted till index I minus 1, it will be simply carried down till DP of I as well. Okay, that means we are not deleting it, hence the maximum that we deleted till I minus 1, it will be for the I as well. So the DP of I will be simply DP of I minus 1. Okay, now what about the case where we delete a subarray ending at nums of I? Okay, so we delete a subarray ending at nums of I. So that means we had a subarray at I, and now we need to delete this segment. Okay, we delete a subarray. That means we will delete some subarray. Suppose this is j, so we'll delete some subarray j till I, whose sum percent k is equals to 0. Okay, we'll delete it, and now there can exist multiple such j's. So what will be the DP of I? DP of I will be simply what? Maximum of, we have j less than I, such that like sum of j till I percent k equals to 0, and will be doing what? It will be like DP of, means since we remove this segment, so we'll find out the sum accumulated till DP of j minus 1. So DP of j minus 1 and plus like sum from j till I. Okay, so for all j we'll see this and we'll be like getting the maximum value. Okay, now the next step is to find out this sum, means find out first we need to find like this sum should be divisible by k. So we need to find these j's in optimal time, right? This is the first step, and as well as we need to be able to find this prefix in like a constant time, because obviously like since n can go up to 1 is 5, so we cannot go through like for all i's we can move backwards in direction and see whether the current sum is divisible by k and then try to remove it. Okay, so we obviously cannot do that. So hence we need to find this in optimal time, and we know that whenever we want to find the range sum in constant time, we'll be using prefix sums. Okay, So simply like sum of j till I, it will be what? It will be prefix of I minus prefix of j minus 1. Okay, this is all we'll have for this. Now we also need to make sure that this sum, means this sum that we have, is divisible by k. That means this prefix of I minus prefix of j minus 1 percent k should be equals to 0. Okay, so these j's we need to find. So that means it will be simply what, if we rearrange, so prefix of I percent k, it should be equals to prefix of j minus 1 percent k. And now we all know that we try to bring information in the form of variables we already have, so that on the basis of that we'll be able to calculate pre-computed information. So for particular current I, we know we have this info as well as we have k info. Okay, so now we need to find j's such that whose, means if we current remainder, if the current remainder is what, prefix of I percent k, then we need to find those j's on left, those j's on left, j1 j2 j3 so on the left, who also gave like this prefix of j minus 1 percent k equals to this, the same, means it should be the same. Okay, so hence like the final formula will become like, it will become dp of I will be what, it will be like max j such that dp of j minus 1 plus prefix of I minus prefix of j minus 1, right, and comma the case of dp of, means we will be skipping it. Okay, and in this case we need to find this maximum of j. Okay, so this is the current formula that we have. Now we see like this j can change here. So obviously we need to store, like what if we could pre-compute some information so that we are able to get this maximum j in optimal time. Okay, this is the goal here. So let's try to analyze this formula. So we have the I here, we have I here, we have j here, and we have j here, and both the indices are same only, j minus 1 j minus 1. So let's try to bring them together. Okay, so what we will have, it will be same only dp of I minus 1 and comma, it will be like simply dp of j minus 1 minus prefix of j minus 1. Okay, we have brought these together, which are belonging to the same index, plus prefix of I. Okay, so this is the dp of I that we have currently, the max of these two values. Now we know that we need to find such j, maximum j, max j, such that this value is maximized, means dp of j minus 1 minus prefix of j minus 1 is as maximum as possible. And these j will, how we'll find that these j should have like prefix of j minus 1 percent k should be the same as current remainder that we have. That is, the current remainder was prefix of I percent k. Okay, so hence the final formula that we have is what, dp of I equals to maximum of dp of I minus 1 comma this dp of j minus 1 minus prefix of j minus 1 plus prefix of I. Now obviously if we want to like find this in constant time or optimal time, then we cannot go through all the j's. So we need to pre-compute some information to find this maximum j. So since we have bring the information in the form of a single variable, so what if we store this information, like for the current remainder, for this current remainder we store, like create a max diff of remainder which stores like the maximum value that we have got till now, so with difference like dp of j minus prefix of j. Okay, so for each remainder from like 0 till k minus 1, we store this value, like what is the maximum value that we have got for this. So since we'll be calculating dp at each step, okay, we'll be moving from 0, so we'll be calculating this dp, means dp of I will be calculated, and we also know this prefix of I. Okay, so we will be able to know like this value. Okay, so hence for future remainders, the current remainder that we'll have, for suppose it was x1, so for this x1 we'll be updating like a max diff of x1, will be updating with it with max of whatever value was stored previously comma this value. Okay, dp of I minus prefix of I. Now once we are able to know for the current remainder that we have, what is the maximum value of this formula, then we're able to simply add this maximum value to the prefix of I and take maximum at each step, and hence we will be able to know the maximum sum of deleted elements at each index I. Okay, so what are the two values that we need to calculate? The first value will be simply the dp. The current prefix sum will be able to we means change the prefix sum formula to this max diff formula, because we needed two informations at a time, dp of j minus 1 minus prefix of j minus 1. Okay, so hence we tried to create a new vector which denoted for each remainder, because we need to also make sure that this condition should be satisfied. Hence for each remainder we try to create a separate array which stores the information of dp of j minus prefix of j for each remainder from 0 till k minus 1, and hence we'll be able to get this in constant time, and hence we'll be able to calculate each dp result in constant time. So hence we'll simply need to iterate for I from 0 till n minus 1, and will be in the end we'll get like the maximum sum for till the entire array will be dp of n minus 1. So the minimum sum that we'll be getting is simply the total sum of all elements minus dp of n minus 1. Okay, so this will be the final result. So I hope like you were able to follow along like how we try to like develop the formula of the transitions, how we try to bring the values which had the same index together and then try to like pre-compute. This is what we generally do in like most of the problems involving prefix sums. We try to create formulas such that all the indices which we already are aware of are put together, and then we can like bring information in the form of same index so that like we can pre-compute easily. So that is what we try to do here, and then like we derived that for each remainder we need to store this information dp of I minus dp of prefix of I. So we'll be pre-computing that information as along we are means computing the dp, and then we'll be able to like calculate this result in constant time. So I hope this is clear. Let's see the code once so that it becomes more clearer in your head. So this is the code for this. We have initialized the dp with 0. So dp of I stores the maximum derivative sum for the prefix 0 till I. Okay, and this max diff we have created for each remainder will be able to know like dp of j minus prefix sum of j. Okay, and for each remainder we will be storing the maximum value. So we have initialized it with a very small value so that we take maximum at each. Now currently when we have not processed anything, the prefix sum is 0, as well as means this dp value is also 0, means the maximum derivative sum, and the prefix is also 0. So hence for 0 max diff of 0 will be 0 only. Okay, because remainder currently is 0 only, and this is important for if we want to remove this segment 0 till I. Okay, we want to remove this entire prefix, then we should be able to know like the prefix of j minus 1 should j will lie here, so j minus 1 will be lying here. So this helps us store the information when we remove the entire prefix. So this is like we use it every time whenever we whenever we want to like count the number of sub-arrays which satisfy some conditions. So we initialize this with whenever for the we'll be removing the entire prefix, then for that we create this information so that a valid index is means valid value occurs for that. Okay, so we have the current prefix as 0. Now what we'll do, we iterate through for I from 0 to l minus 1. Now we'll increase our current prefix, find out the remainder that we have currently. Now the option A is to do not delete, so it will be simply dp of I minus 1. So if I exists, then it will be dp of I minus 1 l 0, and the second option is to delete a subarray ending at current index I. So that means it will be simply max diff of remainder, that means dp of j minus 1 minus prefix of j minus 1 plus prefix of I. Okay, so it will be max diff of remainder plus current prefix, and for dp of I it will be maximum of both of these options, and then we'll need to update this max diff array for the current remainder that we have. So for the current remainder that we have, we'll be updating it with the result already stored comma dp of I minus current prefix, and then the final result will be stored in the current prefix sum will be storing the sum of all the elements of the array, and will be deleting this maximum sum that we have to get the minimum sum of remaining elements. And the time complexity, as you can see, like we have used big of k space for this and big of n space for dp, and k can go up to 1e5, so space is big of 1e5, and this means dp calculation we are doing in big of n, and all the further calculations are in constant time. So the space as well as the time complexity is of the order of big of 1e5, which will be running in approximately very less than 1 second. Okay, So I hope like you were able to follow the approach, how we like the first step was to why think about DP, because we each element had a choice of either getting included in the subarray that we are deleting or not, and then we try to move in the direction of what transitions we have. So either an element will be deleted or not be deleted, then on the basis of that we try to see the formulas that we'll be creating, and then we try to play with the formula by means moving variables here and there, and then try to bring information in the form of single variable. That is what we do in most of the times, and then we will are able to simply solve the problem. So let's try to submit the code as well here, and this is the same code that we discussed. Let's try to submit it and see how much time it takes to run, and it should run pretty fast, and it runs in 52 ms, which is very fast for like order of 1e5 complexity. So yeah, this was the entire approach and explanation for this problem, and I hope like by now you are like a pro in prefix some type of questions, and are able to like derive results on your own and solve problems on your own. And if you are able to do, then make sure to like as well as subscribe, and if you yet have any doubts remaining, feel free to comment down. I will be happy to respond. Thank you so much for watching.